All right, so today we're just going to continue on with our discussion of NMR. We are going to talk a little bit more about splitting. We're going to look at some more or less first order splitting patterns, complex splitting, and try to analyze how they would arise. And then we are going to start looking at some spectra. So we'll work through, we'll do at least one where, one step sometimes is not really trying to propose a structure, but just assigning the spectrum, the peaks to a molecule. We'll go through a few kind of easier examples, and then we're going to look at just a couple more techniques. They're not really, they're a little bit different than what we've done so far. Okay, and then that'll pretty much finish up our initial discussion of just one-dimensional proton NMR. And then the next thing after that will be C13 NMR. Okay? All right, so let's start in by looking at a first order splitting pattern. This one has a splitting tree on it already, but if we were looking at this in the absence of that tree, what we would usually do, so notice that it's very symmetrical. So for one thing, that means it's first order, but the other thing is that if it is a single signal, it should be relatively symmetrical, and it's not like two overlapping signals or something like that. And so the main thing we start to do is look toward the outside of the splitting pattern. And so we might look at the outside two peaks, and we would notice that these are in a 1-to-1 ratio. Okay, so that means right there is that we have a component of a doublet within our splitting pattern. So we should be able to see that distance, that coupling, this 1-to-1 in other places throughout the signal. So that splitting should match this one, this to here, should match here to here. It would match from here to here. And the same on this other side. So all of these splittings are arising from a single doublet. Okay? And if we wanted to, measure what the coupling constant was, well, we don't really, these are in hertz. We would just, estimate, or we'd get a number, whatever, these values, and we just subtract to get the size of the doublet. Okay? So the next thing we could look at then, we could go back and collapse each of those, right? So we'd bring those two together to here, to here, to here, and they're all collapsing back to this point. The next thing we might look at is that these two here, the size of these two here is roughly a 1-to-3 ratio to the next biggest peak. So if that was 1, this is 3, this is a 3, these two are 1, 3, 3, 1, 1. So if we have a 1-to-3 ratio, that means that we have to have some component of a quartet. Okay, so then we can bring those together, right? So this shows all of those coming together into quartets. And then we have one more big coupling. So if we looked from one doublet or something like that, so let's say from here, and we looked all the way through, I think, to here, that's too big. I think it's to here. These would be the same left-hand piece of another cortex. So we have this doublet here. That would be the similar to this one. So this, and then doublet, doublet, doublet. So that makes, here's a doublet. This is a quartet. 1 to 3 to 3 to 1. Okay. 1 to 3. Oh, no, 1 to 3 to 3 to 1. And then from 1 to 3 to 3 to 1. So there's two big quartets. So the other coupling, this one here, should match where I have that one drawn, or it could be drawn from here to here. Right? Or you could do it on the other side from, say, here to here. So that would be the big doublet. So essentially we have one big doublet. It's split into quartets, and each of those are split into doublets. So we could call, this, I'm not always sure. I always kind of just do these, I think the small ones first, but so doublet of quartets. I'm not really sure if there's a rule on the order, because we kind of analyze this as a doublet and then a quartet and then a doublet, but whether it's a doublet of a quartet of doublets or a doublet of quartets or a quartet of doublets, I'm not sure if there's a rule about if you do them in the order of the size of the coupling constant or, something like that. All right, so can everybody see those components in here? So let's look at another one. This one's a little bit simpler.
Is it always like this, clear and...
What?
Is it always like this clear and...
No, it's never this clear. Yeah, these are probably simulated spectra. But we'll look at one that they're pretty clear. That's a real spectrum. Okay, so again, if we look at this one, what would we see first if we did it in the way we did the last one?
A doublet.
Yeah, so we have a doublet component over here, right? And so then that's the same distance as this, and this, right? So we have a doublet, and I guess we could draw it the way they did here. We could bring these two back, each of these back together, because these are 1 to 1, and then the next ratio is probably 1 to 3, right? So, 3, 1, so then it's just going back into a quartet. All right, so we got a doublet of quartets. All right. All right, so there's one more thing that can cause a second order coupling that's a little bit different than what we talked about already. And this has to do with what's called magnetic equivalence. So magnetic equivalence is when we have chemical shift equivalent nuclei coupling equally to the other protons in the spin system. So, for example, these two protons here are magnetically equivalent. Well, they're chemical shift equivalent, right? And each of these are going to couple to each of the protons on the methyl group equally, okay? So that's fine. That's what we normally see.
And integration increase, I think, this way. Does integration increase for the methyl groups?
The methyl group would have a bigger integration, right? It'd be a 2 to 3 ratio in the integration. Okay, but this is talking about more about the splitting. Yeah. Okay, so magnetic non-equivalence causes, I that again. I hit something with my hand down there.
Is it the bottom left corner? This little magnifying glass?
No, that. Oh, yeah. Okay. But, interesting. Causes second-order effects, magnetic non-equivalence, and this happens when chemical shift equivalent nuclei couple unequally to other protons in the spin system. So, for example, if we look at this molecule here, what we might notice is that there is a plane of symmetry through the molecule like this. And so these two and these two are chemical shift equivalent to each other. Okay? However, if we look at this red one, it's going to have one coupling to the green proton next to it, but it could have some small long-range coupling to the other proton in that same spin system, right? So one proton here can couple to two other equivalent protons with a different coupling constant to each of those protons, right? Because this would have one coupling constant here, call this, say, J1, and it would have a different coupling constant to this proton, J2, even though those two protons are chemical shift equivalent. Yeah?
Does J2 only show up because the green protons are chemically equivalent? Or magnetically equivalent?
Well, no, it could show up if we had a different substitution pattern here. Then it could still show those couplings. But if they weren't, if the two green ones weren't equivalent, then it wouldn't cause magnetic non-equivalence. So if we had something like this, so if this was the chlorine like we have there, the OH, and if we just had something else over here, a methyl group or something, then this proton here, the one that was in red, could have these two couplings, this one and this one, right? But these two are no longer equivalent. So that's, this would be a magnetic equivalent situation, not magnetic non-equivalence, because these two are different. But in this case, these two protons are equivalent to one another, but each of them has a different coupling constant to this other one. Okay, we'll look at another system, but this causes some weird second-order effects to peaks. So, for example, here's a molecule at the top that is similar to the one that was on the previous side, is this para-substituted benzene ring, and what we would normally expect is that because it's this para-substitution, that each of these would just be a doublet and a doublet, right? Because they're only coupling to it only has one main proton next to it. But because we have this situation where A couples to X, and A can have a different coupling to X prime, so we could have J AX does not equal J AX prime, then we end up with these second order effects, which are these like small peaks and stuff down here. Okay? So in these cases, I think oftentimes what we can more or less do is kind of ignore these small peaks and just look at the bigger ones. So we could just call this a doublet, even though there's this, shaggy stuff at the bottom. And this one we could call a doublet, and then it kind of fits what we might expect for a para-substituted, a first-order para-substituted one. This bottom one looks a little bit even more complicated. So again, this should have a plane of symmetry. Well, it does have a plane of symmetry through the molecule like this. So these two protons should be chemically shift equivalent. And these blue ones should be equivalent as well, right? Because they're related by, they're homotopic. They're related by a plane of symmetry. Okay? However, if we take one of these red ones, it's going to have one coupling constant here, call it 1, and it's going to have a different coupling constant to here. Right? So that it couples to both of the blue protons, but with different coupling constants. So this is the magnetic non-equivalence. And so where we might expect, in this case, remember that these blue protons, because they're equivalent, will not couple to each other, right? So again, we might expect this one just to couple here. Would be a doublet, but but when it's coupling also over here, it might be a doublet of doublets. If it wasn't symmetrical, it would be a doublet of doublets. But because this coupling to the two red ones, and the two red ones are equivalent, it causes, again, this kind of second order stuff with these small peaks down here at the bottom and some weird splitting on the tops of those. But again, if we kind of ignore this bottom stuff, then we could just call this a doublet of doublets. Right? Ignore this small splittings here, too. And double. And so we would just be seeing this split, kind of an ortho coupling and a meta coupling. Okay, but they are more complicated than what we would expect here. So a lot of times when we look at these spectra, you kind of gloss over this stuff, right? Because it's hard for us to actually predict these. And even like that program that we looked at last time, I guess maybe we can put in non-equivalence like that. I wonder if that thing is still... So, to do this, it seems like we would have, let's see here, let's move these a little bit apart. But the difference would be that these two are chemical shift equivalent, but the coupling constants would be different. So let's say this one is 6. I don't know if this will show? No, so that just shows a doublet of doublets. So it doesn't really show any second order effects.
Would a higher well, I mean, if a higher frequency, you could just see the splitting on the actual peaks, right?
Well, I think that's what we're seeing here. This here, so this is 6 hertz, right? And then the bigger one is 8 hertz.
Oh, that's right, yeah.
So all it's showing is just a doublet of doublets. It doesn't pay attention that these are, yeah. So I don't know how we simulate that kind of.
Can you increase the magnetic strength?
No, that's used.
Well, I think if anything, that would reduce any second order effects. If we go down the other way.
I frequently get it backwards.
Well, yeah, look at this one. So this is showing like a splitting there, but it doesn't match the coupling constants over here, right? So that's actually some kind of second order effect right there. Because, yeah, the second order effects are usually going to get greater the lower the field. Right, and we remove some of that at higher fields. So let's see if we go back up to 800. I don't know why they're necessarily all sloped to the one side, though. You know, sometimes you get this experimentally just because of how the peak is sampled, like the number of points, because these lines are usually drawn from points, and if you don't have enough points to draw the top of the peak up like this, it can go from one point to the next. But I don't know why it would be doing it here. Oh well, okay. Okay, so I guess the bottom line here, we know sometimes the peaks, especially in these aromatic systems, don't always come out as perfect as you might expect them to be. Contrary to what we were just talking about, whether all of our multiplets and stuff here are so perfect. What is this? Oh, are we going to simulate this one? I didn't think I had that on here. I didn't. All right, I guess this is one that I'd simulated before on the same website down there. So if you want, you could go and try to set this up and see how it turns out. And then you can vary it with field, you can vary it with chemical shift differences or any of those kind of things. Okay. All right, so let's go on to try to assign some peaks here. So here's some peaks that are pretty complicated looking. You can see the splittings very well. You notice that some of them are sloping a little bit to one side or another. That kind of means that they're a little bit second order. And we can talk about that as we go through them. So I think if we just want to do the assignments, notice the way it is here, that the spectrum's pretty small at the bottom, but then it kind of goes, this is a higher frequency range, right? And then it goes down. And so they have these in frequencies. So it goes this way and then this way. Okay, so the highest frequency here would be the highest chemical shift down here. Right? And then we have this stuff here, and we just keep moving down like that. Okay, so here's a molecule. You can see that okay. So I think that, that the first thing you want to do if you want to assign some of these is you want to like pick out some type of unique positions on the molecule that might have a characteristic chemical shift, or in this case, a splitting pattern, and try to start by identifying one of them in there.
Well, the isopropyl is going to be a septet.
This one here?
The middle proton.
Well, it would be a septet from these two methyl groups.
And then there's another.
But there's another CH2 over here. And in fact, that CH2 there is next to a chiral center.
Oh, no.
So these are going to be diastereotopic. So this would be like a doublet of septets or something like that.
Yeah.
Or a multiplet.
That's what I like.
So where's the most complicated signal in the whole spectrum?
550 hertz.
Yeah, this one right here. Right? So that's one way I think we could assign it like that. So this would be H2. All right? And it's a little, more complicated than we can analyze.
H10 would be a singlet, right?
H10, well, there's 2 protons up there. So it could be a singlet, but because there's not really a plane of symmetry down through the middle here, right? We have this double bond over here, and we have different stuff over here. And so, if I was just looking at the molecule, I'd probably expect those 2 protons on H2, or the 2 H10 protons to be different.
Okay.
Where would they show up in the spectrum?
750 hertz. Because there's 2 doublets.
The 750 here. Well, 750, that's going to be this one that's down at 2.5 parts per million. So if we look at the actual spectrum with the parts per million, so H10, where do we think it would be?
I mean, around 4. Yeah, but even squinting at that doesn't look right.
No.
Because that's CH2.
Oh, could it be? I guess would it be around 5?
Yeah, it's probably be one of these ones around 5.
Okay.
Okay, so we have around 5. We probably have... So we have these 2 on the end of the double bond here, and we have 2 that are on the end of the double bond over here as well.
Okay.
Right? And so we have all these double bond protons that are all going to be like above 5. All right, so out of those, we have 2, 3, 4, 5 protons on the double bonds. We have 1 proton signal here that stands out all by itself. Which one do you think that will be? Why does that keep doing that?
It's all by 10.
Well, which out of those looks the most different? We have these 2 on 10, we have this 1 on 7, and we have these 2 on the end on 8.
Well,
So we're expecting those 3 to be the highest chemical shift, right?
Well, one of these, I would say there's 2 on this end, there's 2 on this end. Those are more similar to one another than this one that has more high substitution.
So you're saying at 1550 hertz.
Right? And if we look at that proton, this H7, and we have these 2 H8 protons, we should see two different couplings here as well. We have this kind of cis coupling here, and we have this trans coupling over here.
I thought that was a ring this whole time.
Oh, you did? Oh, sorry. Yeah, there's no bond between here.
Okay. All right, we're back on the same page.
Okay, so H7 would have two coupling constants like this, so it should be a doublet of doublets. And so that's probably this one out here. Right, so it would have two coupling constants. It would have one that's this size, and it would have one that's from here to here, or from here to here. Right, so which of those, the red one or the blue one, would be the cis coupling?
The larger J would be cis, so the blue one.
The smaller J is the cis.
I'm forgetting all of my rules.
So the trans coupling, yeah, was like 15 to 17, and the cis is more like, 10 to 13 or something. Okay, so the red one would be the cis, and this blue would be the trans coupling. Okay, so then if we wanted to identify the H8 protons, they should have matching coupling constants, right? So if we wanted to find a peak that's down in this range that matched these, we could say, we could take that blue one, the blue coupling that I drew out there, and see where it matches in this spectrum, other ones. So what I used to do is just take something like this because I'm old-fashioned. I have hard copies of things. And you could just hold this up here, and you could draw a line here and here, the size of this, and then you could just slide it over here, and then notice, it matches those two right there. Right. Or if you slide it over here, doesn't really match, well, maybe. Might match something there, not to here, or, so probably this one then has the same coupling as that blue one, so this is an H8 that's trans, so that would be this one over here, right? And if we wanted to find the cis, we could do the same thing, but we mark the size of the cis coupling. See, so it doesn't match that. Probably doesn't really match here. It's probably here and underneath that big one there or something. So to me, it looks like the red is something like here to something under there. Right, so it's going to be overlapped. I guess that's not what I had in my notes, but that's what it looks like here. Do that again. So it's that small one here. But yeah, it doesn't really look like it matches that. So it's got to be over under there. Okay. So that red there has to be the other H8. Okay, and then we have the other two H10 protons. Okay, so what about the coupling between the two protons on the ends of these double bonds. So between 8 and 8 here. Here, let's draw these. I'm going to draw these. So that's cis. I'm going to draw this one in red, H8. So that's the red ones there. So what about coupling between these two on the ends of the double bond?
It's gonna be very small.
Very small, okay? In fact, we won't really see that very much, okay? And likewise, for the two protons on H10, they won't couple much to each other. So what I would say is that this is probably then an H10 here, and there's another H10 there, which the red H8 is overlapping with. You know, so it's not 100%, but I think by matching those other two and then this one here, right, this one's taller than everything else, and that's because it has a component of this one underneath there. So that would be my best guess or proposal. Maybe not a full-on guess. Yeah.
Both 8/8s are doublets of doublets, right?
Both H8 are mostly just doublets because the coupling to each other is very small.
Oh, so it's
Yeah, and so, well, if I didn't draw on there, they do look a little shaggy on there, and they're a little bit broadened. So sometimes when you have a real small coupling like that, it'll just make it look a little bit broader, shorter. Yeah, and likewise here, right? This has got some kind of coupling, but then that could have not only the coupling between them, but it can have a little couplings as well. So there's some other small couplings that are going on in there too. Okay, so what's the next one that would be the most unique?
The or H4.
H4, right? So where do we think that would show up? So here we have, this is H7, this is H8, we have an H10 in here, and we have an H10 and another H8. So where would H4 be?
A little bit less than 4. It doesn't match up with the splitting, because like even if like it should be a triplet of triplets, right? Because it'd be n+1 for the coupling for 5 for H5, and then it'd be
Right, but remember, this proton, this position right here is a chiral center. So when we have a chiral center, the CH2 groups on each side are likely to be they are diastereotopic, and they're likely to have different chemical shifts. And when they have different chemical shifts, that means they're non-equivalent, and so they will each couple differently to H4. Right? So what we're likely to see is that there's two from here, and they're each going to be coupling to here. So it's going to be a doublet of doublets, of doublets, of doublets.
so 450 or 400.
Well, just think about the chemical shift. This is a proton on a carbon with an alcohol, with an oxygen. And if we look at any of these down here,
Maybe only at 4.
it's got to be the one near 4, right?
I just don't like the splitting pattern.
Right. Well, there's going to be some
Overlap.
overlap of those peaks. But this one has to be H4. And so, yeah, there's going to be 4 different coupling constants. And so it looks like from the way the spectrum is, some of those might be multiples of one another. You know, if one's 2, the other one's 4 or something. And so they're kind of overlapping, but not every one. Okay, so that's H4. And then notice down here, they kind of split these in a bad way. So notice that this is second order aiming to the inside. This one is going to that side. This one is going like this, and this is going like this. Okay, so what that tells me is that each of those pairs, this pair and this pair, are for diastereotopic protons. Okay, and their chemical shifts are kind of close, and so they're tilted towards each other. Okay, and you can see it down here too. This is tilted this way, this is like this is like this is like this. Okay, we already said that this is H2. So this is going to be, each of these are going to be a CH2 group. Okay, so we've got the CH2 that's at C5, and we've got the CH2 that's at C3. Okay, so which of those are going to be at 2.5, and which one is going to be at 1.5?
2.5 is C5, right?
Yeah, because it's an allylic one, so it's next to the double bond, and it's next to the OH. So this has to be the H5. And then this one down here is going to be H3. Right? And both of those, you know, so this would be essentially a doublet of doublet of doublets. Because we have 2 doublet of doublets, and they're kind of overlapped in the middle like this. Same with this other one, but you can actually see, maybe you can see, I can see it here, that in the middle they're not quite superimposed. These are kind of superimposed right in the middle one. But we have a doublet of doublets of doublets. Okay, so that's the same kind of doublet, doublet, doublet. Same here if we count the little small ones, but this one looks more like, well, this one looks more like a doublet of doublets. I think that there might be a tiny coupling inside here on these, but we can't really see it. Like this one, these here, see that little couplings in there? And so those would be, let's see, so H5 would be here. Yeah, it looks like it should be mostly a doublet of doublets, right? Maybe it has some allylic coupling up to H10. Okay. And for H3, those should be very clearly, they're going to couple to each other, so that's a doublet. And they couple to H4, that's a doublet, and to H2, that's a doublet. So a doublet of doublet of doublets. No way. Those you could see those.
Well, you can see it on that sample. On my samples, no.
Right. All right. So we only have one last position here. This one down here looks just like a triplet, but there's nothing that really looks like it should be a triplet, right? And so over here on the right side is kind of an experiment they ran with some different solvents. So down here is the one that we're seeing over here is just in deuterated chloroform, and it looks like a triplet. But if they start to add some deuterated benzene, then it starts to pull apart and apart and apart. And so what we see that this triplet is really is really just two doublets. Okay, so the two methyl groups, in fact, have different chemical shifts. Okay, so these H1 and H9, or methyl 1 and methyl 9, are different from one another. Why would that be?
Alcohol group?
Yeah, because the alcohol, the chiral center. So those, let's see, we're going to draw this, are also diastereotopic. So they have different chemical shifts. Okay? When it's just in chloroform, they have their two chemical shifts, but they're just overlapped in the middle. Right? And when we vary the solvent, you change the solvents, then the chemical shifts can move around and stuff in different solvents. Right? So it just happens as we add more benzene, then those move apart. And so we can see them as two separate doublets instead.
Wouldn't they move together? Because if you moved it, well, I guess it depends on how you never mind. I'm gonna stop talking.
What do you mean?
So it could be the way that you have the doublets assigned. Yeah, it makes sense that they would go apart, but couldn't you also say that they move together and you still have that same splitting pattern? But instead of assigning those four peaks, like one on or a methyl on one side and methyl on the other, you could just say that they're close enough that you have a methyl here and a methyl here. So you still have the same splitting, like at 100% benzene, but they're just a little bit overlapping, or they're coming together.
Well, I think in 100% benzene, we have two doublets like this, right? And as it goes to chloroform, those two are moving together until the middle one is overlapping. Right? And that's why it shows up as a 1 to 2 to 1 ratio, because the middle peak of both of those doublets is overlapping right there.
Yeah, but I mean, you could do the same. You would get the same thing if you just moved it like that.
Right. So what we would have to do to tell whether the doublets are as I drew it here, or if it's like from here to here, right, and from here to here, right? So what should be happening is that the chemical shift should be changing, but the coupling constant should remain the same.
Yeah, okay.
So I would just say that it looks like to me that what I've marked as those looks the same as this. You know, these look like the chemical shifts to me. I mean, the coupling constants to me. But I didn't measure them out or anything. I could do that here. Let's do the same old-fashioned trick here. Well, and that assumes that they're all plotted exactly the same, too. So if I put this here and then one in the middle, so I just did it halfway there, and I go up here, then that matches the left two, and the left two, and the left two.
Okay. Yeah, it makes sense. Interesting.
But you're right that it could have, it's just it's kind of the luck of the draw, basically. That, they just happen to be like this in deuterated chloroform. It could just as well be we change the solvent and they move the other way, or this way. It's, I don't think you can really predict how the spectrum is going to change when you vary the solvent. You just have to try. And this is kind of a trick that if you have, a spectrum that has a lot of overlapping peaks, that's hard to interpret. Sometimes you can just vary the solvent and you might just luck out and they move apart. And then you can analyze it more easily.
Okay, cool.
But yeah, you can't really predict so much what direction that they'll move, or you might luck out those might move apart, but they didn't tell us what the rest of the spectrum looked like in benzene. Maybe all the other ones just moved on top of each other when you went in benzene. We don't know that.
Yeah, because I guess, the reason why intuitively it seems like they would, if you varied it, it wouldn't. I would find it obviously that's not the case. Obviously this is not the case, but I would have thought that if you'd varied the solvent, they would get more. They would become more. The shifts would become more equivalent.
Mm-hmm.
But obviously that is not the case.
I think that's just hard to predict.
Yeah, that makes
We
sense.
could put it in deuterated methanol or acetone or some other thing too, and just see where the solvents are going to move, where the shifts are going to move. I think you just can't really predict that.
Yeah, that makes sense.
Yeah. All right. Something here. So notice, in fact, here in this one, I forgot about this. Look at the integrations here. So 1, this is like, what did we say? 4 probably. 1, 1, 1, 1, 1. And what about this one? We assigned it as 1 proton, but look at it, it's twice as big. So in fact, this one I think has the OH underneath it.
That makes sense.
This one. Let me see if I can find what I was looking for. Oh, it's not, so clear here. So notice, let's look at this one here. This peak here. So notice I drew the arrow like this because this doublet of doublets here is bigger than this doublet of doublets here. And that's because the big coupling here is going over to this one. That's the most second order one because this is the diastereotopic pair, and that geminal coupling is the biggest coupling constant. Okay? But notice when you look at these other ones, like this to this and this to this, they have other splittings. Oops, shoot. That are going in the opposite direction. This one's going this way, and this one's going this way. See what I mean? These small couplings are second order pointing the other way. So that tells us that the second order couplings are going to a peak over here. Okay? Notice that these second order ones here are going the other way. So what would that, but there's nothing really over there. Because that's here. Yeah, so maybe that didn't work on those though. But yeah, sometimes it's not, not just the whole thing slanting in one way. If there's more than one coupling, one could be slanting this way and the other smaller couplings could be going this way. Right? So sometimes that's some bit of information that you can gather as well. All right? All right, so let's just look at some other simple ones here. This gives us a molecular formula, and there's just 3 peaks. So what do you see here, and what would you notice if you were doing this?
I see 2. Initially, I see 2 triplets and a sextet.
Okay, so sextet. Okay.
But it doesn't.
There's a little bit of splitting in all of them.
Yeah, but because the fact that there's 7 carbons means that. Well,
I could you be the triplets are really big. You got a lot of protons on them,
no.
but they have the same shifts.
Right, what about the integrations?
They're
2, 2, 3.
Yeah, that's what I would say too, right? 2, 2, 3. Right? So we have two triplets. So essentially we have to have something that's this is a CH2 group, and it's a triplet, it has to be next to a CH2, right? And then over here, we have a methyl group, and it has to be next to a CH2 group, right? And so this CH2 group and this CH2 group have to be the same. So what we're basically seeing is just a propyl group.
And then you connect them together.
Right, and so because we have 7 carbons, we need at least 2 of these. Symmetrical, like this. And we need something in between. Right, so, yeah, so to come up with a molecular formula, because we have 6, we have 1 more carbon, we have to have really a carbonyl in there. So we have a carbon we don't see. The other thing that might help to start out trying to solve like this is being able to calculate out the number of unsaturations. Right? Because that would have told us, if we came up with 1 unsaturation, it would have told us we had a double bond or ring or something in it already. You don't like that?
I've never liked the degrees of unsaturation. I tell my students to do that, but I've never really liked that.
You have to embrace it.
I know.
Okay, so the way that they tell you, like in just Gen Chem, like in the book, I think they're teaching with or OChem, is that you compare this, to C7 to the saturated system, right? 2N plus 2. So that would be C7H16, right? You compare 14 and 16, difference of 2. Right? 16 minus 14 equals 2. You divide that by 2, you have 1 unsaturation. Okay. So it just tells you that there has to be either a double bond, a pi bond, or a ring. Okay? Let me give you a different way to calculate out unsaturations. Maybe you'll like it better then.
Maybe.
I forgot things on that one.
Well, you throw in the halogens into the equation, and it just is like, I don't care enough.
All right. Well, we're going to do it.
Fair.
You're the student. I'm telling you, you got to do it.
Okay, listen, I'll do it.
All right. So let's just look at what we were just talking about. The maximum number is Cn of hydrogens, 2n plus 2, right? And we have every loss of 2 hydrogens equals 1 unsaturation, or site of unsaturation. And the ways that we can account for those are either rings or pi bonds. Okay? All right, so we're going to use this equation. The number of unsaturations equals the number of carbons minus the number of hydrogens divided by 2 plus the number of nitrogens divided by 2 plus 1. Okay, and so halogens are included as hydrogens because they have the same bonding and valence and everything. The only way you can put a halogen is by taking off a hydrogen, so you just count them in with that. And if you had other, atoms. If you had a silicon on there, it would be included with carbon because it has the same valence as carbon. If you had a phosphorus, same as nitrogen, like that. Sulfur would be the same as oxygen, just whatever is in line in the periodic table. All right? So let's see how this works. So what if we had something like C7H8O? How many unsaturations are there?
7 minus 4 plus 1. So it's 4.
Unsaturations equals 4. Okay, so what does that tell you if something had 4 unsaturations?
There's 4 double bonds or 4 rings or some mixture.
Or, 4 double bonds, 4 rings, or some combination of the two. And so from a practical point of view, what does it mean structurally? What's the most likely way or the easiest way to come up with 4 unsaturations?
Conjugated ring.
Right, a benzene ring. Right, because a benzene ring has 3 pi bonds and a ring, so that's 4 unsaturations. Right, so for this, you could easily have something like this. Or you could have a OH and a methyl group, or you could have a CH2OH, or, all those would be consistent with 4 unsaturations. Okay, so there's obviously other ways to come up with other structural ways to come up with 4 unsaturations as well, but especially when you have molecules this size, it's difficult without a benzene ring. Okay, so what if we had something like C6H7N?
No, I don't know how to do math.
That's what right at you.
Yeah, so it's
We got
6 minus 3
plus 1.
3.5 plus 0.5. So 2.5, 3, 4.
4.
Yeah, I don't know.
Right, so I think it's best to just do it sequentially, I think. 6 minus 7 halves. So I just think 6 minus 3.5, right, is what, 2.5, plus a half is 3, plus 1 equals 4. I think you end up wrong if sometimes people try to add these two together. But that doesn't work because this is a negative and this is a positive. Right, so for me, not being a super mathematician either, it's easier to just subtract this one, then add that one, and then add, right? And not try to add some of these together in the middle. Get rid of that half as fast as possible. Fractions, so this could be consistent with something like aniline, right? 4 unsaturations. It could be consistent with something like a pyridine with a methyl group on it. Something like that. So no, I think that calculating the unsaturations is just one more piece of information for our puzzle, right? And if you can immediately say, there's likely a benzene ring or there's got to be something like that in it, then, I think it's several wise to just use, let's go back. Right, so Andrew, let's do that one. to use whatever information you have available, and to toss some out that you ignore some data that you have is unwise.
Maybe.
All right, so this one looks more gnarly, probably because it's at 100 megahertz or something. What about unsaturations?
0.
0. Okay, C7H. So what kind of functional groups could we have? We have 1 oxygen.
The alcohol.
It could have an alcohol.
Ether.
Ether.
That's it, right?
Yeah, I think that's all right. If you look at the, this already says right there, though. I should have blocked that out.
Well, I mean, couldn't that just be contamination or like a wet sample? Because like in chloroform, water shows up at a
Closer to
small amount-
1.5
a
or
small
something.
amount
Yeah.
shows up, but the more you add, the more it
Right.
travels.
Yeah. So, yeah, that's an issue you got to take into account,
Yeah.
right? At least be open to.
Yeah.
Um,
Okay.
because a lot of times, too, the OHs, and depending upon your solvent, may or may not show up. Or they'll be very broad. In fact, that brings up a point that, if we see an OH, or if we see what could be a water peak can show up, that depends upon the solvent and everything else on whether we can assign it that way or not. In this one, it's labeled as an OH, so that tells us, right off that I guess if we follow that it's not an ether. Is there another way that we could likely say that it's not an ether?
No symmetry.
Right? There's no symmetry. We don't have to have a symmetrical
That's true.
ether.
You don't.
Would it polarly shift? Yeah.
Well, we have one downfield shift. Let's look at these integrations. What do you think? If we have this integration versus this,
Oh, it's 1.
if this is 1, this is probably just 1. So if you have an ether, unless you have a quaternary center on one side of the ether, there should be more protons that are downfield, right? But we have only 1 proton on a carbon next to an oxygen. So if we have an alcohol, we decided we could just draw out what are the possible, alcohols. So could we have something like this?
No.
No, because we only have 1 proton there. Okay, so this likely means that it's a secondary alcohol. So we could have an alcohol here. We could have alcohol here. What about here?
Not really.
Well, no, I could just be lying. Well, no, because like that forest at 1.5, it means that there's a lot of distinct signals, and if it was symmetrical,
Right.
you'd be able to resolve some of it.
Yeah, so this is symmetrical, so likely it's not that. I agree, because it looks like our spectrum is more complicated than that. So we'll take that out. We probably don't have a bunch of branching either. It looks like we have a bunch of CH2 groups in here. I think if we figured this out, if that was 1, this is probably 6. because those are likely to be methyl groups, right? So these are going to be, we have to have 2 methyl groups. So we're kind of left with these 2 in the middle here. What do you think about those 2?
One on the right.
The one on the right?
Yeah.
Why?
Because it's asymmetrical. Well, I get both of them. It makes more sense. I can't figure out.
They're 2 triplets. They're at like 0.9.
Right, so we could have one here, here, and here, and then the other one like here, 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 and they're kind of just, they're overlapped in there. But it could be like there's a doublet and then a triplet.
Yeah, which would be the left one? It was a double triplet.
Mm-hmm. So what do you think about this chemical shift? It's all the way down at like between 0.8 and 0.9. Does that fit for both of those?
Yeah.
I think that this one, being next to the alcohol, it would shift it further downfield. So this one would likely to be more like 1.2 or something. So that would move it. You know, you'd have some kind of a doublet over here. So I would agree that this one seems like the better one because the 2 methyl groups would be more similar or they would be more overlapped. That's the main thing, I guess. But yeah, it's a little hard to see because it's real. Keep this messy in there. Okay, what about this one?
A benzene ring.
Yep, benzene ring. Let's see if I can figure out the... You can't really see this. I think it's like this. Okay, so we've got a benzene ring. This and this and this and this. How many unsaturations are there?
4.
4? Hmm?
It's 4, right?
8 minus 5 is 3 plus 1 is 4. So 2 to 3. What about these other ones? 2, 2, and 1. So one hint is usually if there's something that's an impurity, which they never show in these kind of spectra, if there is an impurity, then it usually doesn't have an integration on it.
Wow. If you know it's an impurity.
Right. Okay, so how many substituents do we have on the benzene ring?
Looks like 2? No.
It's 2 to 3. Then we have
How many protons are on the benzene ring?
6.
And 5.
5 from the
Oh,
integration.
so yeah, then there's one substitute.
Okay, look at these 2. This is a 2 and a 2. What do you think about those?
I think that's an alkene.
An alkene? A CH2 and a CH2?
Yeah. That doesn't feel right. It just, 4 screams to me alkene.
Well, 4 is pretty far upfield for an alkene.
Okay.
Because usually they'll start, even if it's a terminal, the protons on the end of an alkene, they're usually like 4.7 or 8 or something. Okay, 4 for me more screams like next to an oxygen.
Okay, and that would make sense.
And we have 2 oxygens. But what do you think these are? So they integrate for 2 and 2, and they have all this splitting, and they're angled like this.
Is it an ester? No, it can't be.
Diastereotype, right?
Well, they're as 2 and 2, though. I think it's just a CH2 and a CH2. Right? If they were first order, they would be 2 triplets. Right? But because their chemical shift has come closer together, remember those simulations or the second order coupling effects we saw the other day? I don't know if I don't have them in these notes. So I think it's just 2 CH2s. They're 2 triplets, but because their chemical shifts are close together, they're second order. Okay, so we have 2 CH2s. They almost have the same chemical shift. We have 2 oxygens, so it's likely between 2 oxygens.
Ether to an alcohol?
Right. So I think it's an ether, CH2, CH2, to an alcohol on the end.
Oh, because at 2 ppm ish.
Well, alcohols can move around a lot too.
Yes.
Right. But because it's just kind of a semi-broad signal with no splitting or anything, usually OHs don't show up splitting either because they can hydrogen bond and they exchange. Sometimes I think if there are like very dilute samples in aprotic solvents where there's very little exchange going on, they can sometimes show splitting. Okay, but typically we don't see that. Okay, so the other thing, let's just finish off by looking at the benzene ring section. Okay, so this little peak here is chloroform. Okay, so the solvent is going to be deuterated chloroform. We're going to talk more about solvents next time. But so we use a deuterated solvent, right, because we don't want a proton signal that's so massive from the solvent, because usually the solvent, if it was just a protonated solvent, it would just swamp out the rest of the signals. But in every solvent, if we get deuterated chloroform, there's a small amount of protonated chloroform in there. So that's what that is. These other signals look like they're a little bit second order. So I would say this is kind of like a triplet. So we have some kind of magnetic non-equivalence, like we were talking about. Then we have like a doublet here and a triplet like under here. I'm just saying partly because I know what kind of a symmetry pattern we have here, right? So in a monosubstituted benzene ring, right, these two will be equivalent, and they're going to be primarily doublets, though it could have some metacoupling as well. Okay? These two are equivalent, and they're going to look more like triplets. Okay? Though, in this case, we're going to have some kind of magnetic non-equivalence as well. And then this one, I guess I'll use yellow, is going to be by itself. So we should have a 1 to 2 to 2 ratio in here. So I think that's what we have here. This is the 1. This one is like a doublet, so this is the ortho protons next to the ether. And this integrates for 2. It's more like a triplet, so that's the one in green. The other way we can confirm this is so the protons ortho to the ether are the most upfield. Or notice that the ortho and the para positions are more upfield. So why would that be? Resonance, right? I think we talked about this before, right? So if we have an oxygen like this that has non-bonding electrons on it, then these electrons can be donated into the ring. So they can go to this position, or they can go all the way to this position. So we end up with a delta minus and a delta minus on these positions, and this one shows a delta minus over here. So when we build up a negative charge, does that cause shielding or deshielding? Shielding, and it moves upfield. And so that's why these two are more shielded. And they're ortho and para to the electron donating group. Okay, yeah.
Just to double check, both the green and the red protons have the magnetic
Non-equivalence. Yeah, I think so, because look at especially the one in green, because it has all this small stuff. It, looks kind of odd, right? And these other ones could be partly, this yellow one should have some ortho coupling and some para coupling. So it should be like a triplet, but then it should be like another triplet, right? So maybe these are little triplets. So this actually could be a triplet of triplets, and that would be, pretty much what it should look like. But the red ones, they look pretty shaggy on there. So I think that's from the magnetic non-equivalence. But they could also have, ortho coupling. But if this has a ortho and a para, that's where the non-equivalence comes from, right? The meta coupling to the yellow one, that is just a first order coupling. The one thing I forgot too, I'm going to stop this and I guess.